Hello friends, I welcome you to part 2 of this episode of Learning Physics, and I am taking you into solve the past paper questions. This is I think going to be part 2. The unit we are dealing with is physical quantities and units or measurements, and we have said that in this unit we are supposed to study a few important or understand a few important concepts about physical quantities, units. Specifically, I am saying we shall be discussing questions. Some of them we have already seen them in part 1, and these include questions about base quantities and units, estimates. We have seen errors and uncertainties in part 1. We shall see them again in part 2. And precision and accuracy, scalars and vectors, of course, not forgetting systematic and random errors, and so many more. So without wasting any time, I would like to take this opportunity to take you to part 2 of solve the past paper questions under physical quantities and units or base units, measurements, errors, and uncertainties. So let's go to the document to solve the questions. So I think we stopped on page 21. I think we had stopped on that question. So this is part 2, and let's start from where we stopped. The intensity of a progressive wave is defined as the average power transmitted through a surface per unit area. That is, intensity is power per unit area. Show that the SI base units of intensity are kilograms per second cubed. So without wasting time, intensity is power per unit area, and the power is work done over time taken. So we shall say this is work done over time, then times 1 over area or over area. We can think of work done as force times distance. So that is force times distance. This is work done. I just want to write W for work done. So this is force times distance over T times A. So it means we know that the base units of force are kilogram meters per second squared, because force is mass times acceleration. Then distance, that is meters. We know time, that is in seconds. Then area, that is in meters squared. So we are now substituting. So the base units of intensity are going to be force, which is kilogram meters per second squared, times distance, which is meters, divided by seconds times meters squared. So meters times meters, that is meters squared over meters squared. M cancels out. So we remain with the kilogram. Meters has cancelled out. S power negative 2 divided by S power 1, we subtract the powers. So that becomes S power negative 3 as required. The intensity I of a sound wave is related to the amplitude x naught of the wave by that expression. Rho is density of the medium. C is the speed. F is frequency. K is a constant. Show that K has no units. So we begin by making K the subject. So K in that expression is going to be the intensity divided by density C F squared x naught squared. We know the units of intensity. Density is kilograms per meters cubed, that is for density. C is speed, so C is meters per second. F is frequency, and F is therefore going to be per second, because frequency is 1 over T. So F is going to be per second, but remember it is F squared, so it will be per second squared. Then x naught, x is amplitude is a distance, so x naught is meters. So I'm now substituting. The units for K will be intensity, which we said it is kilograms per meters cubed, per second cubed from the previous part, divided by rho, which is kilogram per meters cubed, times C, which is meters per second, times F, which is S power negative 2, times x naught, which is meters squared. X naught is squared. So we simplify this. In the numerator, we still have kilogram S power negative 3. In the denominator, we have kilogram m power negative 3 times m power 2. It is m power negative 3 times m power 3, which is 1, or m power 0, which is 1. Then s power negative 1 times s power negative 2, that is s power negative 3. You see that kilogram cancels, s power negative 3 cancels. So we conclude that k has no units. Do not say equals to 1 or do not say equals to 0. You just cancel out and conclude that it has no units. Calculate the intensity in picowatts per meter squared of a sound wave. Pico is 10 power negative 12, I guess. So we substitute. Intensity was given by K rho CF squared x naught squared. We are substituting. K is 20, density is 1.2, C is 330, F is 260, but is squared. X naught is 0.24, but is also squared, but x naught is in nanometers. So this will be times 10 power negative 9. So this is times 10 power negative 9. And this should be, I think this is x naught squared, so that is squared. So I'll press my calculator. 20 times 1.2 times 330 times 260 squared times open brackets 0.24 times, or I will just say 0.24 exponent negative 9, but this is squared. And that gives us 3.08 times 10 power negative 11. But we want the answer in pico. So we divide this by 10 power negative 12. So I'll just say the answer divide by, I will say 1 exponent negative 12, that is pico. And that is 30.8 pico watts per meter squared. So 30.8, or approximately 31. The rate of flow of thermal energy Q over T in a material is given by that expression. So Q over T is rate of flow of thermal energy. So Q is thermal energy, or it is energy. Determine the SI base units of C. So we shall begin with the Q over T. Q over T is energy, which energy, we know energy is work done, force times distance. So energy is kilogram meters squared per second squared. You can find that energy, that is work done, which is force times distance. Force is kilogram meters per second squared times meters. So that is kilogram meters squared per second squared divided by time, which is seconds. So this rate is kilogram meters squared per second cubed, that is Q over T. And then we have area, that is meters squared. We have x, thickness, that is meters. Then we have T, temperature, that is in Kelvin. I think that is all. So we make C the subject. Making C the subject, I'll simply say that C is equal to Q over T divided by or multiplied by X divided by A times T. And now I'm finding the units. The units of C will be kilogram meters squared per second cubed, then times X, which is meters, divided by A, which is meters squared, times T, which is Kelvin. I'll cancel out meters squared there. So I remain with kilogram S power negative 3, and then K goes up. There is one M there, so meters, and then K power negative 1 as the base units of C. A coin is made in the shape of a thin cylinder as shown in the figure here. You see that figure. Figure shows the measurements made in order to determine the density. So we see the units. Calculate the density in a kilogram per meters cubed. So all the quantities should be in SI units. To begin with, we know that density is mass over volume. Density is equal to mass over volume. We don't have volume, but it's a cylinder. Volume is equal to cross-sectional area, which is pi r squared times h, or times the thickness, h. But we don't have the radius, so I must express it in terms of diameter. This is going to be pi d over 2, this is square times h, which is pi d squared h over 4. That is the volume. So I'm substituting for the volume. So density is going to be where there is volume, I put pi d squared h over 4. So it becomes 4m over pi d squared h. Now substitution becomes easy. I'm now substituting. This becomes 4 times the mass, which is 9.6 times 10 power negative 3 to change it to kilograms, divided by pi. Diameter is 22.1 times 10 power negative 3 to change it to meters, but is squared, times h, which is 2.00 times 10 power negative 3 to change it to meters. So having done that, I'll check my calculator. So in the numerator, I have 4 times 9.6 exponent negative 3. I will divide that one by open brackets. That is, okay, I will say pi into brackets 22.1 exponent negative 3, but this is squared, times open another bracket 2 exponent negative 3. So when I divide, the density is going to be 12513.15. I'll just write 12513 kilograms per meters cubed. So the density here is 12513. Okay, you can also press your calculator and verify. Calculate the percentage uncertainty in rho. We have already seen that density rho is equal to 4m divided by pi d squared. So we want percentage uncertainty. Because of division and the power on d, we shall just add the fractional uncertainties. The fractional uncertainty in density is going to be equal to the fractional uncertainty in m plus the power multiplies by the fractional, so that is the twice uncertainty in d over d. So by times 100 this side, times 100 the other side, it will be percentage. So I'll say percentage in rho is equal to, in m is 0.5 over 9.6 plus 2 times d. D is 0.1 Did I leave out something? I think I left out H. Yes, there's H here. So this will be plus H, which is fraction in H over H. So I will multiply this by 100. So this is 2 times 0.1 over 22.1 plus. For H, it is 0. I think 01 over 2.00. I will multiply the whole of this by 100. So I will just check my calculator. 0.5 divided by 9.6 plus 0.2 divided by 22.1 plus 0.01 divided by 2.00. That is the answer times 100. Change it to percentage, that is 6.61%, or approximately 6.6%. State the value of the percentage value of the density with its actual uncertainty. So we have to change 6.6 to absolute. So absolute uncertainty density is going to be 6.6 over 100 times the value of density, which we got as 12,513. So I'll just set that one, divide again by 100, then times 12,513. So this is giving me 827. 827 to one significant figure, it is 800. So it is 800 to one significant figure. And since it ends with two zeros, it is a whole number ending with two zeros. I'll write the final density as a whole number ending with two zeros. That makes this one to be 12,500. Underline all the base unit quantities in the following list. Base quantities. So the current, I think current is base, mass is base, temperature is base. Second is not a base quantity, is a base unit. Charge is not, ampere is not. Ampere is a base unit, not a base quantity. Weight is not. So we have mass, current, and temperature. The potential energy EP stored in a stretched wire is given by that expression. EP is equal to that. C is a constant, rho is sigma is strain, V is the volume of the wire. Determine the SI base units of C. So to begin with, V is volume, the units of V will be meters cubed. Secondly, strain is extension over original length. Strain has no units. And then we have potential energy. Potential energy, the potential energy stored. So potential energy can also be mgh. And that means the units of potential energy will be equal to m, which is kilogram, g, which is meters per second squared, times h, which is meters, making it kilogram meters squared per second squared. So I make C the subject here. C is going to be twice E potential divided by sigma squared times V. So the base units of C are going to be, we ignore the 2, so the base units will be kilogram meters squared S power -2 divided by sigma has no units, so we ignore it, and V is volume, that is meters cubed. V is volume. So meters squared over meters cubed, we subtract the powers. So it is 2 minus 3, which is -1. Therefore, this will be kilogram per meter per second squared. A mass M is placed on the end of a spring that is hung vertically as shown here. The mass is made to oscillate vertically. The time period of the oscillations of the mass is t. The period t is given by that expression where c is a constant and k is a spring constant. Show that c has no units. Let's begin with the spring constant from Hooke's law. Force is directly proportional to extension. In other words, force is equal to spring constant times x. So the force constant K is equal to force over x, or the spring constant is F over x. The base units of K therefore are going to be force, which is kilogram meters per second squared divided by meters. So it means the force constant has units as kilogram per second squared, that is K. Okay. Then of course we have M. M is mass, that is in kilograms, and T is time period, that is in seconds. I'm now substituting after making C the subject, so C is equal to T divided by the square root of M over K. So the units are going to be T, which is seconds, divided by the square root of M, which is kilograms, over K, which is kilograms per second squared. So kilogram has cancelled out. So the base units of C are now seconds divided by the square root of kilogram has cancelled out. We have 1 over S power -2. 1 over S power -2 is the same as S power -2, so that is S power 2. You get the reciprocal of that. Then the square cancels with the square root, so you get S over S, and S over S cancels. You simply conclude that C has no units. You can't say equals to 1, you can't say equals to 0, that would be wrong. Okay. An object B is on a horizontal surface. Two forces act on B in this horizontal plane. A vector diagram for these forces is shown to scale. I will not consider this as being shown to scale because I know, although it is supposed to be shown to, a vector diagram of the forces is shown to scale. I don't think this will be to scale in the process of, I don't think this is the exact size. If it is printed, maybe it will be to scale, but here it may not be the exact size. However, we shall still find the answer. So a force of 7.5 newtons towards the north and a force of 2.5 newtons from 30 degrees north of east act on B. The mass is 750 grams. Draw an arrow to show the approximate direction of the resultant of these forces. If this is drawn to scale, it means on the top of 7.4, I'll just add, on the top of 7.5, I'll add 2.5, Let me see how many centimeters or how many meters represent 2.5. So 2.5 from my ruler, it is about this is 2.8 centimeters. So I will represent this. I'll add 2.8 here. So this is going to be representing 2.5 newtons. I'm joining head to tail. So the resultant will be from the bottom up to that point. I will change the color for the resultant. So the resultant will be here. If this is drawn to scale, I'll just measure this distance to find the resultant. But let's see what the question wants. Show that the magnitude of the resultant force on B is 6.6 newtons. If you measure from the diagram directly, you have first of all measured the length representing 2.5 as 2.8 centimeters. I don't know what length is representing 7.5, but it means the scale is going to be 1 centimeter will be 2.5 over 2.8. Let me see the length representing 7.5. This is 8.4 is representing 7.5. Okay, so it means the scale is going to be either 2.5 divided by 2.8, or the scale will be 7.5 divided by 8.4. I just measured the length representing 7.5, or I measured the length representing 2.5. So the scale is going to be 2.5 over 2.8. That is 1 centimeter represents 2.5 over 2.8 newtons, or 1 centimeter represents 7.5 over 4.8 newtons. So if I want to find the resultant, I just measure this length. So measuring the length, it is 7.4. So the resultant from the diagram, the resultant is 7.4 times the scale, which is either 7.5 over 8.4 or 2.5 over 2.8. So let me check. 7.4 times 7.5 divided by 8.4. So this gives me 6.607 or 6.6 newtons from the diagram. However, they didn't tell us to just use that. You could also use another method, which is maybe the cosine rule. Another method, which is the cosine rule, it means we need the angle between the vectors after joining them head to tail. This is the vector of 2.5, this is the vector of 7.5, and we need this angle here. So if I extend the horizontal line here, this angle is 30, it means this angle is 60 degrees. So since I have the angle between 7.5 and 2.5 after joining them head to tail, it means I can now use the cosine rule. So the resultant force Fr squared is going to be equal to 7.5 squared plus 2.5 squared minus 2 times 7.5 times 2.5 cos of 60. And I will just press my calculator here. So I have 7.5 squared plus 2.5 squared minus, I'll open a bracket, 2 times 7.5 times 2.5. I'm using the cosine rule, remember, cos of 60. So that is 175 over 4 square root. So root of the answer. So it means the resultant force is approximately 6.6 newtons. It is just 1 mark. Calculate the magnitude of the acceleration of B produced by this resultant force. By definition, or by Newton's second law, resultant force is mass times acceleration. So it means the acceleration is going to be the resultant force 6.6 divided by the mass. They gave us the mass as 75 grams, which is 0.75. So 6.6 divided by 0.75, and I think that is 8.8 meters per second squared. Determine the angle between the direction of the acceleration and the direction of the 7.5 Newton force. Of course, the acceleration is in the same direction as the resultant force. If I don't want to calculate, I can use a protractor and I measure that angle. The acceleration is in the same direction as the resultant force, so the angle we want is that one, theta. Let me first use a protractor. So I put my protractor there. And when I put my protractor there, I'm getting, because I drew this on a computer, so my answer may not be very accurate, but at least. So that is 10, 15, 16, 17, 18. So theta from the diagram, it is 18. Theta is equal to 18 degrees from scale diagram. From scale diagram, you can also measure. It is 18 degrees, but I may get a different value by calculation, and by calculation it is going to be the most exact value. So by calculation I have this is 7.5 newtons, and I have this as 2.5 newtons. I have this one resultant as 6.6 newtons. This angle is 60. I want this angle here as theta, so I will use the cosine rule. The opposite side is 2.5. So I will say by cosine rule, I will say 2.5 squared equals to 6.6 squared plus 7.5 squared minus 2 times 6.6 times 7.5 cos of the angle theta. So I want to find theta using the cosine rule. So I'm going to find theta. So I will simply say 2.5 squared is on the left minus 6.6. I'm taking 6.6 squared on the left. I'm also taking 7.5 squared on the left. That's why I'm subtracting. Then it is a negative, so I'm going to divide by this quantity here. So divide by, open the brackets, 2 times 6.6 times 7.5, close the brackets. Remember it was a negative, so I'll put a negative somewhere. Negative. And that gives me a positive value, which is actually that value. But I want the cos inverse. I want the cos inverse of that quantity, so I will press shift, cos inverse of the answer. And it is giving me theta as 19 point something or 19 degrees. So from calculation, theta is 19 degrees. From scale diagram, you could be having a range between 17 degrees to 21 degrees. All those values will be correct. From calculation to be 19 degrees exactly, 19 point something. But from a scale diagram, you'll have a range of values. Okay. Determine the SI base units of stress. Stress is defined as force over area. So stress normally written as sigma, that is force over area. We know the base units of force, kilogram, meters per second squared. We know the base units of area as meters squared. So the base units of stress will be kilogram, meters per second squared divided by meters squared. Meters divided by meters squared, that is meters power -1. So this is kilogram per meter per second squared. Then Young modulus. Young modulus is stress over strain. Young modulus is equal to stress divided by strain. We know that strain has no units. And since strain has no units, it means the units of stress are the same as the units of Young modulus. Hence, the units of Young modulus are going to be the same as those of of stress, kilogram per meter per second squared. Kilogram per meter per second squared. The microphone detects a musical note of frequency f. The microphone is connected to a cathode ray oscilloscope. The signal from the microscope is observed on the CRO as illustrated here. This is supposed to be in waves, but since it is here, we shall answer it. Before we answer any questions, let's first find the length representing one cycle. We can say, okay, starting from, say, this point here, up to this point, although it is not exactly in the center, I think that is not a good point to start with. But I can take this point and this point maybe. This point here and this point, I think these 2 points are corresponding points. I think they can represent one cycle. So we want that length. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There are 19 small squares representing one cycle, but each small square is 1/5 because 1, 2, 3, 4, 5 small squares represent 1 centimeter. So this reading is going to be, I think, 19 divided by 5, that is 3.8. So one cycle is represented by 3.8 centimeters. Let's check also the amplitude. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 small squares on the vertical times the value of one small square, which is 1/5. I think 11/5 is that 2.2? That is 2.2 centimeters. Let's see the questions now. The time-based setting of the CRO is that. Time-based will give us the period. The Y-plate setting is that. That will give us the amplitude. So use the figure to determine the amplitude of the signal. So we have seen that the amplitude scale reading is 2.2 centimeters. We have seen that. So the amplitude is going to be 2.2 centimeters times the setting, which is 2.5 millivolts per centimeter. So per centimeter cancels out, and this gives us 5.5 millivolts. So this is 5.5 millivolts. Oh, let me change the color of the marker. Then the frequency F. We have already seen the period scale reading or the time scale reading. The period scale reading from the graph. My students normally call it L. It was 3.8 in centimeters. So it means the period is going to be the scale reading, which is 3.8 in centimeters times the time-based setting, which is 0.5 milliseconds per centimeter. 0.5 milliseconds per centimeter. So per centimeter cancels out. And this gives us, remember the frequency is the reciprocal, but milli is times 10 power -3. So I have 3.8 3.8 times 0.5 exponent. Remember, mid is power negative 3, so exponent negative 3. So this is 1.9. It's 1.9 times 10 power negative 3. That is period. Frequency is going to be 1 over the reciprocal, so it is 1 over 1.9 times 10 power negative 3. So we have 1 divided by the answer, and that is 526.3. 526.3 as the frequency. So I can write to two significant figures, approximately 530. The actual uncertainty in F caused by reading the scale on the CRO. F is read in the horizontal, and the value which affects the uncertainty in the horizontal is 3.8. So we just quote the uncertainty in reading 3.8. Uncertainty in reading 3.8 centimeters is going to be equal to, we take the smallest reading on the grid. The smallest reading is 1 over 5, which is 0.2. So that will be the uncertainty. Excuse me. So this will be plus or minus 0.2 centimeters. You can also verify from the graph. Because 5 small squares represent 1 centimeter, so the smallest division is 1 over 5. That can be the absolute uncertainty in that reading. So this is 1 small square. So that is the absolute uncertainty. And remember, it is the one which determines the frequency. Note that the frequency was 1 over that reading, which is 3.8, times the time-based setting, which my students normally call x. So the time-based setting has no uncertainty. It is only L with the uncertainty. And when we have division, remember this is like having a quantity in the numerator, L power 0 over L power 1 times x. To find the absolute uncertainty, we use the fractional. So uncertainty in F over F is equal to uncertainty is equal to 0 times uncertainty in L over L plus uncertainty in L over L, because x will not have any absolute uncertainty. So it's like this quantity is useless. So I wanted you to see that absolute uncertainty in F is equal to that in L, which is 0.2 centimeters over the value of L, which is 3.8, times the corrective value of frequency, because we multiply both sides by F. So this will be times 526.3. So I'll just multiply this times 0.2 divided by 3.8. And this is 27.6 or 28. So that will be 28. Then state F with its actual uncertainty. So it means now this uncertainty must be written to one significant figure. And writing 28 to one significant figure, it is called 30. So absolute uncertainty is approximately 30. So F is going to be 530 plus or minus 30. Same number, both ending with 10. The figure shows a turbine that is used to generate electrical power from the wind. So that is the figure. The power P available from the wind is given by that expression. L is length, base units. So it means the units of L squared are going to be meters squared because L is length. Rho is density. The units of density are going to be kilogram per meters cubed. V is speed of wind. So V cubed is going to have units in meters cubed times S power negative 3 because it is speed cubed. C is a constant. P was power. So we know that power is equal to energy over time or work done over time. Work done is force times distance over time. So it means the units of power can be kilogram meters per second squared times meters. Force is kilogram meters per second squared. Then times meters divided by time t, which is in seconds. So the units of power are going to be kilogram meters squared s power negative 3. That is s power negative 2 divided by s is s power negative 3. So let's now substitute. We make C the subject. C is going to be power divided by L squared rho V cubed. So the units of C will be power, kilogram, meter squared S power negative 3 divided by L cubed, which is L squared, which is meters squared. Density, that is kilogram per meters cubed. Then times meters cubed, S power negative 3. We are now rearranging, so we have kilogram meters squared S power negative 3 divided by kilogram m squared times m power negative 3 times m power 3 is simply m squared. Then we remain with s power negative 3. So the terms are cancelling, kilogram meters squared s power negative 3. So we conclude that C has no units. I'm saying don't cross out and say units equals to 0 or units equals to 1. Just cross out the terms and say this has no units. Next, energy is stored in a metal wire that is extended elastically. I think that is in deformation of solids. What is meant by extended elastically? The material is extended elastically if it returns to its original length when the load is removed. So the wire returns to its original length when the load is removed. So when the force is removed and the material returns to its original length, then we say it is elastically deformed. If it does not return, then we say it is plastically deformed. Show that the SI units of energy per unit volume is that. So energy, of course, energy is work done, that is force times distance. So the units of energy are going to be kilogram meters squared per second squared, that is for energy. And then volume, that is meters cubed. So energy per unit volume, so that is energy over volume. Energy over volume will have units kilogram meters squared per second squared divided by meters cubed. So m squared over m cubed is equal to kilogram per meter per second squared. For a wire extended elastically, the elastic energy per unit volume, X, is given by that expression. So X is energy per unit volume. C is a constant. Epsilon is the strain. So we know that epsilon squared, this one has no units because strain has no units. E is the Young modulus. E is the Young modulus. And of course, we know the units of X. X was energy per unit volume, which we have calculated above. X is kilogram per meter per second squared, energy per unit volume. Then Young modulus Young modulus is equal to stress over strain. Since strain has no units, we know that stress is force over area. So the units of stress are kilogram meters per second squared over meters squared. The units are kilogram per meter per second squared for stress. The units for Young modulus are kilogram per meter per second squared since strain has no units. Strain has no units. So the units of Young modulus are kilogram per meter per second squared. So I make C the subject. So C is equal to X over epsilon squared times E. And the units of C will be X, which is kilogram per meter per second squared over E, which is kilogram per meter per second squared. So you see kilogram cancels, per meter cancels, per second squared cancels. We conclude by saying that C has no units. Two wires, each of length L, are placed parallel to each other, a distance x apart as shown in the figure. Each wire carries a current I. The currents give rise to a force F on each wire given by that expression, where K is a constant, times the SI base units of K. So I is current, so I squared will have units as ampere squared. L is length, units are going to be meters. X is, what is X? X is distance between, so X is also in meters. And then we just make K the subject. So K is going to be Fx over I squared times L. So the units of course, we know F is force, whose units are kilogram per meters per second squared. That is mass times acceleration. So the units of K are going to be kilogram meters per second squared times meters divided by ampere squared times meters. So this has cancelled. So I remain with kilogram meters s power negative 2, then s squared going up, it becomes per ampere squared. On the figure, sketch the variation with x of f. The quantities I and L remain constant. So we have seen that f is equal to k I squared L over x. So f is inversely proportional to x. When x is 0, f is infinity, and when f is 0, x must be infinity. So that is a curve which does not touch any of the axes. For x equals to 0, f is infinity from that equation. And for f equals to 0, x is going to be infinity. So the graph does not touch any of the axes. It is exponential to the axis. Then the current I in both of the wires is varied. On the figure, sketch the variation with I of f. From the graph, from the equation, you see that f is directly proportional to I squared. F is directly proportional to I squared. So because I increases more rapidly, so this is going to be a straight line, since as I increases, the square of I also increases. Therefore, the value of f increases. If it was I power 4, then this would be a curve, but this is going to be a straight line. It is going to be a straight line upwards. A metal wire has original length L0. It is then suspended and hangs vertically as shown in the figure. So the elastic potential energy E is given there. as that elastic potential energy. So rho is density. Let's write the units. Density, that is kilogram per meters cubed. G is acceleration due to gravity or acceleration of free fall, which is meters per second squared. A is cross-sectional area, so that is going to be meters squared. C is a constant. Determine the SI base units of C. Let's first of all find those of energy. Elastic potential energy. Energy, I'll use any. You can use any expression for potential energy. You can use mgh or work done, and this can be mgh or work done, and this means the units of energy are going to be kilogram meters per second squared. Because of h, this will also be squared. Kilogram meters squared s power -2. So I make C the subject, and C is going to be energy divided by rho squared g squared al naught cubed. So the base units are going to be kilogram meters squared s power -2 divided by density squared. I'm squaring density, so it will be kilogram squared times meters power -3 squared, it becomes meters power -6. Then times g. G is also squared, so it will be meters squared. S power -2 squared becomes s power -4, which we multiply the powers. Then times cross-sectional area, that is meters squared, times L cubed. Remember, L was, what was L? L was length. L naught was length, which is meters, but is L naught cubed. So it will be meters cubed. So we are now simplifying this. I'll first maintain, of course, m squared can cancel. I can reduce that, no problem. Kilogram reduces with that square. So you have s power -2 in the numerator. In the denominator, you have kilogram m power -6 times m power 2 times m power 3. We add the powers. It gives us m power -1, because it's -6 plus 2 plus 3. Remember, 1m squared has cancelled, so that is power -1. Then times s power -4. So s power -2 divided by -4, we subtract the powers, so that becomes power +2. So that is s power 2. The kilogram goes up, it becomes per kilogram. M goes up, it becomes m power -1 goes up, it becomes m. And then s power -2 divided by s power -4, we have got s squared. So it means the SI base units of C are going to be per kilogram meters s power 2 or seconds squared. You can also verify. Perhaps my algebra may not be correct, but I think it's correct. You can verify. State the most appropriate instrument or instruments for the measurement of the following. Diameter of the wire, 1 millimeter. That is very small. We use a micrometer screw gauge. Or we can use a traveling microscope. Then the resistance of a filament, of course, resistance, we can use an ohm meter. If the ohm meter is absent, you can use a voltmeter together with an ammeter. These two must work as together. One reads the voltage, the PD, one reads the current to find the resistance. Alternatively, you can use a multimeter on an ohm setting. A multimeter set to ohms. a multimeter on ohms setting or ohm setting. You get your multimeter and set to ohms to be able to find the resistance. Then the peak of alternating voltage. We normally measure alternating voltage using a calibrated CRO, cathode ray oscilloscope, calibrated cathode ray oscilloscope. Or instead of a calibrated cathode ray oscilloscope, they are what we call SC voltimeters. They are voltimeters specifically designed to measure alternating voltage. We call them SC voltimeters. Okay. The mass of a cube of aluminium is found to be 580 grams with an uncertainty of 10 grams. Each side of the cube has length. Each side, I'll use L for side, which is 6.0 centimeters. But you know it is a cube. So it means the volume is going to be side times side times side, which is L cubed or side cubed. Calculate the density with its uncertainty. Explain your answer to an appropriate number of significant figures and it is 5 marks. That is very easy. Density is equal to mass over volume, which is going to be mass over L cubed or side cubed. And this is going to be 580 divided by 6 cubed, which is going to be 580 divided by 6 cubed. So this is giving us 2.685 grams per centimeters cubed. So let's find the uncertainty because we have m over L cubed or side cubed. The fraction uncertainty in density should be equal to the fraction uncertainty in the mass plus, because of the power, so we have 3 times the fraction uncertainty in L. So the absolute in density is going to be in mass, that is 10 grams over 580. We don't convert the units because we are dividing, the units cancel out. Plus 3, side is 0.1 divided by 6.0. I'll multiply this by the density because it was in the denominator, so it is times 2.685. And this gives the absolute as, so this will be, okay, I'll say 10 divided by 580 plus 0.3 divided by 6, then times 2.685. I'm getting 0.18. To one significant figure, it is approximately 0.2 as the absolute uncertainty, so this is 0.2. Because it is one decimal place, I'll write the final answer to one decimal place, which will make this one to be 2.7. A metal wire has a cross-section of diameter 0.8. That is a very small diameter. We can measure this using a micrometer screw gauge. You can also use a traveling microscope. State how the instrument in A is checked so as to avoid a systematic error. The most important systematic error here is a zero error. So check for the zero error because you can't check. You can also check for wrong calibration. Check for zero error, but you may not easily check a wrong calibration using a micrometer screw gauge. So check for the zero error because zero error is systematic. How the instrument is used to reduce random errors. We normally reduce random errors in such measurements using the instrument such as a micrometer screw gauge. We take several readings along the object and obtain the average. So take several readings along that's along take several readings along the wire and obtain the average. Okay, for each of the following, tick one box to indicate whether the experimental technique would reduce random error, systematic error, or neither. The first row has been completed as an example. So let's look at this. Let's look at this. Keeping your eye in line with the scale and the liquid level for a single reading of a thermometer. Here you are trying to avoid taking readings from different angles, and that one corrects for random error. Because this one example of random error is, that is supposed to be keeping your eye, although they say it is systematic, it is actually correcting for random error. The second one, averaging many readings. We have seen that averaging many readings caters for us or reduces the random error. The tick is there. Then using a linear scale on an ammeter, whether the scale is linear or non-linear, it does not change anything. So this one does not solve any problem. Then correcting for a non-zero error. Non-zero error is a systematic error. So when you correct for it, you are minimizing a systematic error. So systematic error in the second column, random error in the first column, neither in the third column. The measurements for a particular time interval is repeated many times. The readings are found to vary. The results are shown in the figure here. So these are the results. And they have told us that the true value is 10.1, which I think it is here, 10.1, that is the true value. So it means there is a value below the true value and there are values above the true value. So there is a random error. Number two, the average of these values is, I think it is the peak here, which is 10.3. The average of these values is above the true value. So there could be a systematic error. So let's see the questions. State how the readings on the figure show the presence of a systematic error. So you see the average of the values is above 10.1, is not the true value. So there is a systematic error. So we can say the average or the peak is not the true value. The average or the peak is not the true value. The average or the peak is not the true value. The average or the peak is not the true value. So there is a systematic error. Or you would say the readings are not centered around the true value. The readings are not centered around the true value. You see that the readings are centered the other side. Here the true value is 10.1. So the readings are not centered around the true value, so it means there is a systematic error. Number 2, a random error. We see that there are values above and below the true value, so there is a random error. So we can say values are scattered. Values are scattered, or we see there is a wide range between each of these values, so there is a random error. So values have positive and negative values around the peak value, that is above and below. Values have positive and negative values around the peak. In fact, let me change this to readings. If that is hard, I know you are familiar to values are scattered. Values are scattered. I know you are used to scattering of values due to random errors. So values are scattered. Or they have a wide range. So there is a random error. State the expected changes to the figure for experimental measurements that are more accurate. For more accurate, the average must be moving towards 10.1. Or the peak must be tending towards 10.1. So the peak or the average of these readings, the peak or the average value moves towards or shifts towards the true value. Because remember, accuracy is how close the average of these readings is to the true value. So the average of the readings should be tending towards the true value for more accurate results. Then precise, the range becomes smaller. The bars get closer to each other. So the lines are closer together. The lines are supposed to be closer together. And if the lines are closer together, it means the peak is going to be sharper. So you could also say the peak will be sharper. Okay, for more precise values, the lines are close together, meaning the range is small. So the peak will be sharper. Measurements made for a sample of metal wire are shown in the figure. State the appropriate instruments used to make each of these measurements. Number 1, length. I think 1750 millimeters if I divide by 1000 or by 100. By 100, I think it is 17.5 in meters. Is that true? 1750 divided by 100. That is 17.5 in meters. So we can measure that using a meter ruler because it is even to it can be measured using a meter ruler in the laboratory, or you can measure it using a tape measure. Then diameter of 0.38 millimeters, that is very small. We can use a micrometer screw gauge. Or we can use a digital calipers. Not a normal vernier caliper, but we can use digital calipers. Then resistance, we have already seen resistance is measured using an ohm meter. You can measure resistance using both an ammeter and a voltmeter. because the ammeter will give you the current and the voltmeter will give you the PD. You divide and get the resistance. Or we can use a multimeter. A multimeter on ohms setting. Multimeter on ohms setting. Show that the resistivity of a metal is calculated to be 4.86 times 10 power negative 7 ohm meters. Show that the resistivity is given by that. So we know what resistivity is. We have already seen the expression. Resistivity can be given by R times A over L. And A is cross-sectional area. Since we have diameter, cross-sectional area, which would be pi r squared, is going to be pi d squared over 4. That is cross-sectional area. So it means resistivity is going to be equal to pi d squared times r divided by 4l. So I'm now substituting. So this is pi. Then what was d? D is 0.38 times 10 power negative 3. So this is 0.38. So pi times 0.38 times 10 power negative 3, that is squared. Then the resistance was 7.5 ohms. Divide by 4 times the length was, I think the length is 1.75 in meters. Is it 1.75? Yeah, this was centimeters, this was not meters. Because in meters we divide by 1,000. That is 1,750 by 1,000. That's 1.75 in meters. So this is 1.75 in meters. So I press my calculator then. So from my calculator, I will start with pi times open brackets 0.38 exponent negative 3, and that is squared, times 7.5 divide by 4 times 1.75, and this is 7.86 times 10 power negative 7. Okay, so that is our resistivity. Calculate the uncertainty in the resistivity. So uncertainty in the resistivity, since we have our resistivity as given by this formula here, I'll just take the absolute uncertainty in resistance will be in D, which will be twice fraction in D plus in R, which is fraction in R, plus L, which is fraction in L. I ignore all the constants, so this will be times the resistance rho. So I'm now substituting. This will be 2 times 0.01 from the table. I mean from the table, 0.01 over 0.38. You don't need to convert the units because they will cancel, plus for R is 0.2 divided by 7.5 for resistance, plus for L it is 3 divided by 1750. This is going to be multiplied by the value of rho we obtained above, which is 4.86 times 10 power negative 7. So I have to check this with my calculator. So this is going to be a 0.02 divide by 0.38 squared, close the bracket, plus 0.2 times 7.5, close the bracket, plus 3 divided by 1750, close that bracket. Answer is that one, times 4.86 exponent negative 7. Getting 7 point, let me check this again. 3, 0.1, 0.2. So I have 2 times 0.01, that is 0.02, divided by 0.38, plus 0.2 divided by 7.5, plus 3 divided by 1750. That is the answer, times 4.86 exponent negative 7. So I think this is true. That is 3.98 times 10 power negative 8. So I can even write it here, 3.98 times 10 power negative 8. Use the answer to express the resistivity with its uncertainty to the appropriate number of significant figures. So I'll write this to one significant figure and the same power as this one. So writing this to power negative 7, I'll move to the left. So it becomes 0.398 times 10 power negative 7, which is 0.4 times 10 power negative 7. So this is one decimal place, 0.4. So this one I'll also write to one decimal place, that is 4.9 in brackets times 10 power negative 7. The volume V of a liquid that flows through a pipe in time t is given by that equation. Determine the SI base units of C. P is pressure. The base units of pressure, that is force over area, which is kilogram meters per second squared divided by meters squared, which is kilogram per meter per second squared, that is pressure. Then R is radius, that is in meters. Because it is R power 4, it is meters power 4. Then C depends on the frictional effects of the liquid. L is length, base units of L, that is meters. So V over T is volume over time. The base units will be meters cubed divided by seconds, meters cubed per second. So let's now find the base units of C. I'm making C the subject, so C is going to be pi times P times R power 4 divided by 8L times V over T. So the units of C are going to be P, kilogram meters per second squared. No, it is kilogram per meter per second squared for P. Then times R, I'm ignoring all the constants. R is m power 4 divided by L, which is meters, V over T, which is meters per second, meters cubed per second. Meters cubed per second. So meters times meters cubed cancels with the meters power 4. So you remain with the kilogram meters power negative 1. S power negative 2 divided by S power negative 1, you get S power negative 1. You subtract the powers, S power negative 2 minus negative 1, that is S power negative 1. So the answer here is going to be kilogram per meter per second. The volume V of a liquid flowing in time t through a pipe of radius r is given by that equation. P is the pressure difference between the ends of the pipe of length L, and C depends on the frictional effects. So they have given us V over T, they have given us P, they have given us R and L. Calculate this value of C. So let's find C. We make C the subject. We have already made C the subject. So C is going to be equal to pi times P R power 4 divided by 8L V over T. So I'm substituting now. So this will be pi times P. P is 2.5 times 10 power 3. Then R is 0.75. We change it to meters. That is times 10 power negative 3. But this is raised to power 4. Then over 8 times L. L is 0.25 in SI units. Times V over T, which is 1.20, but it is times 10 power negative 6. So we now press our calculator. Let's press our calculator. So in the numerator, it's better if you are not good at pressing, you start with the easiest. But I'll simply say pi times 2.5 exponent 3 times 0.75 exponent negative 3, but this is raised to power 4. Where is power 4? Power 4. And that is it. Divide by 8 times 0.25 times 1.2 exponent negative 6. So this is giving me 1.035 times 10 power negative 3. So C is 1.035 times 10 power negative 3. Then calculate the uncertainty in C. 8 and pi will not affect the uncertainty, so we shall just get absolute uncertainty in C is going to be that in P over P plus 4 times that in R over R plus that in L over L plus absolute in V over T divided by V over T. And the whole of this will be multiplied by the value of C. So absolute in C is going to be equal to, for P, I think P is 0.05 divided by 2.5. We don't need to multiply with the power of 10 because they will cancel out. Plus 4 times R, for R I think it was 0.01 over 0.75, plus I think for L was 0.01, I mean 001, divided by 0.250, plus for V over T I think it was 0.01 divided by 1.20, and this is going to be multiplied by C, which is 1.035 times 10 power negative 3. So let's check this in the calculator. I will say open the bracket, 0.05 divided by 2.5. That's 1, plus 4 times that, I'll just say 0.04 divided by 0.75 plus 0.001 divided by 0.25, then plus 0.01 divided by 1.2 or 1.20. That's what I have, times the value of C, which is 1.035 exponent -3. So this is giving us 8.89, 8.9 times 10 power -5. Since they just want uncertainty in that part, that is fine. But for the next part, we now have to use the rules. We have to write this to the same power as the true value. So how do I write 8.9? So the absolute in C is equal to 8.9 times 10 power -5. So this is going to be 0.0, I'm moving 2 steps, 1, 2, 0.0889 times 10 power -3 to have the same power as C. To one significant figure, it is 0.09 times 10 power -3. Those are 2 decimal places, 0.09. So I'll write the answer to 2 decimal places. Also, it is 1.04. But this is times 10 power -3. Make estimates of the following quantities. A sheet of paper. Imagine how many papers fit in 1 millimeter on the ruler. They could be approximately 10, so you can say 1 divided by 10, that is 0.1. So you can, I expect that the thickness of a paper will be between 0.05 up to 0.15. I have said 10 papers can fit in 1 millimeter on a ruler. So that means the thickness can be approximately 1 divided by 10. 1 millimeter divided by 10, which is approximately 0.1. So for me here, I'll quote 0.1 in millimeters, but is between 0.05 to 0.15. The speed of the time for sound to travel 100 meters. We know time is distance over speed, which is 100 meters. The speed of sound is approximately 330. When I press my calculator, 100 divided by 330, that is approximately 0.3. So this is approximately 0.3 to one significant figure. But actually the time can be between 0.25 up to around 0.5 seconds, depending on the choice of the speed of sound in air. Then the weight, we know that weight is going to be mg, and mass is density times volume, so that will be times g. 100 centimeters cubed of water, we know the volume of the density of water, so this is going to be, this is the volume, so that is 1,000 centimeters cubed times 1 gram per centimeter cubed, which makes the mass to be actually 1,000 grams, which is 1 kilogram. So this is going to be, the mass is going to be 1 kilogram times 9.81. So which is going to be approximately 9.81, but remember it is an estimate. So your value of weight can be between 8 newtons up to around 12 newtons. You choose a value from there. Me, I will just choose 10 or 9.8. A sphere of radius r is moving at speed v, radius r, speed v, density rho. The resistivity force F acting on the sphere is given by that expression, where B and K are constants with no units, they are numbers. State the SI base units of F. F is force, that is kilogram meters per second squared. Rho is density, that is kilograms per meters cubed. V is speed, which is meters per second. Use base units to determine the value of K. So we have F is equal to B R squared rho V power K. So F is kilogram meters per second squared. B has no units. R is meters squared. Rho is kilogram per meters cubed. And V is meters per second. So we can use, but V is raised to power K. So this is meters per second raised to power K. I will use M. So on the left, I have M power 1. On the right, I have M power 2 plus negative 3 plus K. Equating the powers, 1 equals to negative 1 plus K. So it means K is equal to 2. Alternatively, I can use S. On the left, I have S power negative 2. On the right, I have S power negative K, which still shows that K is equal to 2. So the answer here is 2. The spacing between two atoms in a crystal is 3.8 times 10 power negative 10. Instead, the distance in pico. Pico is 10 power negative 12. So we just divide 3.8 times 10 power negative 10 divided by 10 power negative 12. So 3.8 exponent negative 10 divided by exponent negative 12. So that is 380. Then calculate the time of 1 day in megaseconds. So 1 day, we know that time of 1 day is 24 hours times 1 hour is 3,600 seconds. But we want the answer in mega, and mega is 10 power 6. So we divide this by 10 power 6. So we have 24 times 3,600. That's what you have, divided by 1 exponent 6. And that is 0.0864. 0.0864. The distance from the Earth to the Sun is 0.15 Tesla meters. Calculate the time in minutes for light to travel from the Sun to the Earth. So we want time. And time is equal to distance. Time equal to distance over speed. So the distance is 0.15 Tesla, terameters. That is times 10 power 12. Tera is 10 power 12. Divide by speed, because it's light, that will be 3 times 10 power 8, speed of light. This is going to give us, so this is going to be 0.15 exponent 12 divided by 3 exponent 8. So that is 500. That is in seconds. We want the answer in minutes. Remember, 1 minute is 60 seconds, so we divide this by 60. So this will be 500 divided by 60. And that is 8.3. Underline all the vectors in the list below. Vectors, we have momentum, we have weight, the rest are scalars. The velocity vector diagram for an aircraft heading due north is shown to scale. This is still shown to scale. The figure, there is a wind blowing from the northwest. So they are saying the speed of the wind is 36 meters per second and the speed of the aircraft is 250. It is drawn to scale. Draw an arrow to show the direction of the resultant velocity of the aircraft. So since it is drawn to scale, I'll just extend. Remember, the vector must be joined head to tail. So I'm just going to transfer the velocity of the wind. I'm just going to transfer the velocity of the wind or extend it further. But remember, it is drawn to scale, and I'm seeing from my ruler, measuring the length of the line representing the wind. It is showing 2.3. I mean 2.4. So I'll extend this downwards 2.4 centimeters. Because it is drawn to scale, I have to extend it 2.4 centimeters downwards so that I have head to tail. Yes. So 2.4 centimeters is around here. So I have this vector of the aircraft upwards and I have the wind in that direction. So I just join here. The space is not enough for me. So I'll try to minimize this first. So the resultant is going to be a line drawn there. Mine might not be very accurate because I'm drawing on a computer, but that is the resultant. This angle here is supposed to be very small because it is to scale. You measure this length here. So you just transfer it here so that you have a complete triangle of head to tail. If I try to extend this, I can even tell that this angle is going to be 45. This angle is 45 degrees. This one is, they say this is 250. And they say that this is 36. Okay, so that is the arrow. The arrow is going to be to the right. Then determine the magnitude of the resultant velocity of the aircraft. So since the diagram was drawn to scale, I have tried to reduce its size. So it means the length has changed. Let me see. 1 centimeter, what does 1 centimeter represent? From the scale, I'm seeing the scale here. So the wind, let me use the vertical one. 250 meters per second from my graph, from my computer, is represented by how many centimeters? So from my computer, I've scaled this down and it is approximately 12. It is approximately 12, actually 11.9 centimeters. That is 250 meters per second, approximately 11.9 centimeters from my computer. That means 1 centimeter is representing 250 over 11.9. 1 centimeter from my computer, not on your paper. For you measure from your paper, but our answers will agree. So 1 centimeter will be 250 over 11.9, or approximately 12. Then I want to find the resultant. Since I just measured, I just extended the other line. Since I've reduced the size, let me measure the other line again. For wind, it is now 1.7, so it should be 1.7 here. Yes, 1.7. So when I join, 1.7 is there. So I'm now measuring again for the resultant from where it starts from at the bottom up to the other line. So I'm measuring the length of this line represented as R. So that is 10 point, that is 10.5.6. So that is 10.6. So R is represented by 10.6 centimeters. I multiply by the scale, which is 250, divided by 11.9. So 10.6 times 250 divided by 11.9. So this is giving me 222. 222.6 or 222.6. So that would be meters per second. But of course, from construction, there could be errors because when you print, it is not the actual size. Let's try to see by calculation. We're going to find a resultant by calculation from this triangle. I'll just use, I can use the cosine rule. They didn't specify the method. I can use the cosine rule since it is joined vector, it is joined head to tail. So R squared is going to be equal to 250 squared plus 36 squared minus 2 times 250 times 36 cos of 45. Then I'm going to find the square root. So that is by the cosine rule, cos of 45. So let us see. So 250 squared plus 36 squared minus, I'll put a bracket, 2 times 36 times 250 cos of 45. So that is what we get, square root. When you get the square root of the answer, it is 225 or 226 meters per second by the cosine rule, since they didn't specify any method. I'm going now to use resolving. I'll use resolving. So if I resolve, I'll just write the answer approximate 226. If I resolve in the vertical, I have f in the y. So in the vertical, there's 250 upwards, 250 is upwards, minus. When I resolve the wind, it will point downwards. That will be 36, either cos or sine, because the cos of 45 is the same as the sine of 45. So it will be 36, maybe sine 45. That is downwards. So that is the difference. Then I find f in the x. It means I have to resolve 36 in the x. I can't resolve 250 in the x because it's only in the vertical. So in the x, it is 36 cos of 45. 36 cos 45. So I now find a resultant. Since they are at 90 degrees, one is in the vertical, one is in the horizontal, I use Pythagoras theorem for the resultant. So the resultant is going to be the square root of 36 cos 45, but it is squared, plus 250 minus sine of, sorry, this is 36 sine, minus 36 sine of 45. Let me try to make this clear. So I'll check with my calculator. So I say open brackets 36 cos 45 squared plus open brackets 250 minus 36 sine of 45, that is also squared. Then we find the square root. What have I done? 36 cos of 45, that is squared, plus 250 minus 36 sine 45, and the whole of this is squared. Then square root of the answer. So this is 225.98, which is approximately 226. So you can use any method that you think is easier for you. Define density. Density is mass over volume. The figure shows a pyramid, a solid pyramid with a square base. So they have given us density, the height. They have given us x, that is the length of each side of the base. Measurements are taken as shown in the table. So the values are shown there. They are not in SI units. Calculate the absolute uncertainty in x. This is 4 centimeters, 5%. So absolute uncertainty in x is equal to 5 over 100 times x, which is 4.0. And this is 5 times 4 divided by 100. That is 0.2. The density rho is calculated from the measurements in the table 1.1. Determine the percentage uncertainty in density. So we go back and find the expression. This is the expression. So density, I'm making density the subject from that expression. So you see that density is going to be 3 times m divided by h, x squared. Now I'm finding the percentage because of division and multiplication. We just ignore 3, which is a constant. So percentage in m, in rho, is going to be equal to percentage in m plus percentage in h plus, because of the power on x, we shall have twice percentage in x. So they gave us the percentages. So this will be for m, it is 2%, plus for h, which is 4%, plus 2 times 5. And I think that is 16%. So the percentage uncertainty is 16%. The square base of the pyramid in B rests on the horizontal surface of a bench. Use data from the figure to calculate the average pressure of the pyramid on the surface. So we know that pressure is force over area. This time the force will be the weight of the pyramid on that area. And we know that weight is mass times acceleration of free fall over area. So this will be the mass. What was the mass? The mass is 19.5. Then G is 9.81. The base was a square base. So I will say base squared. So this is going to be mg over the base squared, because it's a square base. So that was 19.5 times 10 power negative 3 to change the mass to kilograms, times 9.81 divided by the base squared, that is 4.0 times 10 power negative 2, but this is squared. I hope that is the base. The base is x, which is, it is a square base, so it is x times x, that is the cross-sectional area. Let's press the calculator to see the value of pressure. So this is going to be, open the brackets, 19.5 exponent negative 3 times 9.81 divided by 4 exponent negative 2, and this is squared. So I'm finding the pressure as 119.6. So pressure is 119.6, which is approximately 120. A property of a vector quantity that is not property of a scalar quantity is direction. For example, velocity has direction but speed does not. State 2 other scalar quantities and 2 other vector quantities. To start with the vector quantities, there are 6. One has been mentioned, velocity. The others are force or weight. You can talk about moment. You can talk about momentum. They only wanted 2. I will give you all the 5 remaining. You can talk about acceleration. You can talk about displacement. So these are 1, 2, 3, 4, 5 plus velocity. Those are 6 vectors at your level. Then the rest are scalars. Talk about time, talk about mass, talk about distance, talk about temperature, talk about resistance, talk about current. So everything else is a scalar at your level apart from those 6, which are vectors. State 2 properties that are possessed by both scalar and a vector. So whether it is a scalar or a vector, they both have magnitude, that is a number, and then a unit. Determine the magnitudes of the components of the velocity of the ship in the north and in the east direction. So we resolve this to the vertical. I think to the vertical, V in the vertical will be equal to 13 cos of 35. And I think that is, what is 13 cos 35? That is 10.6. Then V in the X, that is east component, V in the X is going to be 13 sine 35. And that is 7.5. So this is 7.5. So these values will be 11, approximately 11, and this is 7.5. So those are the components. The ship now experiences a tidal current. The water in the sea moves with a velocity of 2.7 meters per second to the west. Calculate the resultant velocity component of the ship in the east direction. So the water in the sea moves with a velocity 2.7 to the west. The ship now experiences a tidal current and moves 2.7 to the west. Remember, to the east it is 7.5, and the water in the sea moves with a velocity of 2.7 to the west. Calculate the resultant velocity in the east direction. So that is going to be 7.5 minus 2.7. 7.5 minus 2.7, and that is 4.8. Use your answer in B Roman 1 and B Roman 2 to determine the magnitude of the resultant velocity. So in the east, we have 4.8. And of course, in the north, it has not changed. In the north, we have 11 or 10.6. So since they are at 90 degrees, we use Pythagoras theorem to find the resultant. So V resultant is going to be equal to the square root of 11 squared plus 4.8 squared. So square root of 11 squared plus 4.8 squared. And that is 12.00, so that is 12. Use your answer in B Roman 2, Roman 1 and Roman 2 to determine the angle between the north, remember the north has not changed, and the resultant velocity. This was the east, the resultant is in between the two. So this is the resultant. The north is 11 meters per second, and the resultant is 12 meters per second. So we want to determine the angle between the north and the resultant velocity. Let me see the north. The north is 11, and the resultant velocity, to determine the angle between the north and the resultant velocity of the ship. So I think the resultant is 12. Therefore, we want the angle here, which is opposite. I think opposite is this one, which is 4.8 meters per second in the east. This is opposite. It is in the horizontal. It is the same as this one here, 4.8. So opposite adjacent, that is tan. So the angle theta is going to be the tan inverse of opposite, which is 4.8, over adjacent, which is 11. So I press my calculator. So tan inverse, shift tan inverse of 4.8 divided by 11. That is 23.5, which is approximately 24 degrees. Define density. We know that density is mass divided by volume. A smooth pebble made from uniform rock has the shape of an elongated sphere as shown here. The length of the pebble is L. The cross-sectional area of the pebble in the plane perpendicular to L is circular with the maximum radius R. A student investigating the density of the rock makes measurements to determine the values of L, R, and the mass M of the pebble as follows. So L, R, and M. State the name of the measuring instrument suitable for making these measurements of L. So let's try to change this to centimeters. 0.1242 times is in meters, centimeters times 100. 0.1242 times 100. That is 12.42 in centimeters. So these are two decimal places in centimeters. So it is in most cases going to be measured using a vernier caliper. Vernier calipers because of the two decimal places rather than a meter ruler. It would be a meter ruler if it was one decimal place. Determine the percentage uncertainty in the measurement of R. Measurement of R, percentage uncertainty, so percentage in R is going to be 0.004. There are three zeros. 0.004 divided by the value of R, which is 0.0420, then times 100. 0.0004 divide by 0.0420 times 100, which is 0.95, or approximately 1%. The density rho of the rock from the pebble in B is composed is given by rho equals to m r power n over kl. N is an integer, k is a constant with no units, that is equal to 2.094. Use SI base units to show that n is equal to -2. So on the left we have density whose units are kilogram per meters cubed. On the right we have mass, which is kilograms. We have radius, which is m or n. K has no units, I'll ignore it. L is length, which is in meters. So if I try to use m power -3 should be equal to m power n minus 1. So -3 is equal to n minus 1, which means that n is equal to -2. Then calculate the percentage uncertainty in rho. So it means rho is going to be written as m. Because r is to power -2, I will take it to the denominator. So it is over KL r squared, because it was power -2. Then the percentage uncertainty in rho is going to be equal to the percentage in m, which is going to be delta m over m, plus percentage in k. K has no units, it is a constant, so its uncertainty has also not been given. We shall ignore it, but r is squared, so it is twice r over r. We don't subtract uncertainties, plus delta L over L, and this is times the value of rho. So we substitute, or not times the value of rho, times 100, because this is percentage, it is times 100. So they gave us above there, they gave us the values here. L is that, R is that, M is that. So I'm just going to substitute them here. So for M, that is 0.001 divided by 1.072 plus 2 times 0.0004, I think, divided by 0.0420, then plus L 0.0001 divided by 0.1242, I think. Then this should be multiplied by 100 to change it to percentage. So I'll just check with my calculator. Open brackets, 0.001 divided by 1.072 plus 2 times 0.008. I will just multiply it there directly, so that it will become 0.0008 divided by 0.0420 plus, again open brackets, 0.1231 divided by 0.1242, close the brackets. So that is the sum times 100, that is 2.1 or 2.08, or approximately 2.1% or 2.0, that is 2.1%, not 2.0. So determine the absolute uncertainty. I think now that we have the percentage, absolute is very easy. So let's first find the value of rho. Rho is going to be the mass, which is given in the table. It is given above there as 1 0.072, it was I think in kilograms, divide by K. They have given us K above there as 2.09. So that is 2.094 times L. L was given as 0.1242. Then R was given as 0.0420, but this is squared. So we just substitute in our calculator. So we put this in our calculator. So this is going to be 1.072 divided by, I'll open my bracket, 2.094 times 0.1242 times 0.0420 squared. And that is giving me the density as 2336.7. 2336.7 kilograms per meters cubed. So the absolute uncertainty in density is going to be the percentage, which is 2.1 divided by 100 times 2336.7. So I'll just say times 2.1 divided by 100, which is 49 approximately 50. So this is 49 approximately 50 to one significant figure. So this is 50. So it is a whole number ending with 0. So I'll write this as a whole number ending with 0. So it becomes 2340. A unit may be stated with a prefix that represents a power of 10 or submultiple. Power of 10 multiple or submultiple. To complete the table, to show the name and symbol of each prefix and the corresponding power of 10, multiple or submultiple. So tera is 10 power 12, that one we know. Then this is pico, and pico is small p. In the following list, underline all the units that are SI base units. SI, we have the ampere for current and the meter for length. We don't have coulomb, we don't have the Newton. The potential difference V between the two ends of a uniform metal wire is given by that. D is diameter, I is current, L is length, rho is resistivity. For a particular wire, the percentage uncertainties have been given in the table. So those are the percentage uncertainties. For this value of rho, which is given as 4.1 times 10 power negative 7, calculate the percentage uncertainty. So let's first find rho, making rho the subject here. Rho is equal to pi d squared times v divided by 4l times I. That is rho. So rho equals to pi d squared times v divided by 4l times I. So percentage in rho is going to be twice percentage in D because of the power on D, plus the percentage in V, plus the percentage in L, plus the percentage in I. So it is going to be 2 times for D, which is 3 plus 3.5 plus, and that is 2.5 plus 2.0. That is 6 plus 6, that is 12. I think that is 14%. Then the absolute is very easy. Absolute uncertainty in rho is going to be percentage, convert it, divide by 100 times the value of rho, which is 4.1 times 10 power negative 7. And from my calculator, 14 times 4.1 exponent negative 7 divided by 100. So that is 5.7, which is approximately 6 times 10 power negative 8. Then state what is meant by work done. Of course, we know work done is force times displacement in the direction of the force. Force times displacement in the direction of force. Use your answer in A to show that SI base units of energy are that. So since work is equal to energy in motion, that is force times distance, we know that force, it is just one mark. So I'll just say force is in kilogram meters per second squared and displacement is in meters. So it means the units of energy, which is work, are going to be kilogram meters per second squared times meters, which is kilogram meters squared per second squared. A metal rod is heated at one end so that thermal energy flows to the other end. The thermal energy E that flows through the rod is given there. A is cross-sectional area. The units of A are going to be meters. T1 and T2 are the temperatures of the ends of the rod. So that means the units of T1 minus T2 will actually be Kelvin. L is length. The units of length are going to be meters. We don't subtract units of the same quantity. We don't add or subtract units. So I know people would say K minus K. It doesn't exist. L is in meters. Then we have T. T is in seconds. So then E is energy, which we have already obtained above. So I want the SI units of C. Let's make C the subject. So making C the subject, C is going to be equal to E times L divided by A into T1 minus T2 times T. We're now getting the units. So the units of C will be E, which is kilogram meter squared per second squared divided by, or times L, which is meters, divided by A, which is, A was area, meters squared, then times K, then times seconds. And when you simplify, M squared has cancelled. So we remain with kilogram. There is one M remaining. S power negative 2 divided by S, that is we subtract the powers, so it is S power negative 3. And then 1 over capital K, it becomes K power negative 1. In the following list, underline all units that are SI base units. SI, we have the ampere, this one is not. Kilogram, the Newton is not. The figure shows a horizontal beam clamped at one end. Sorry for the size. The figure shows a horizontal beam clamped at one end with a block attached to the other end. The block is made to oscillate vertically. The angle modulus E is given by this expression here. M is the mass of the block, T is the period, and K is a constant. A student determines the values and percentage uncertainties of K, M, and T, and they are given in the table here. The student uses values of K, M, and T to calculate the value of E as that. Calculate the percentage uncertainty and the value of E. So since we have a formula here for E, it is already made the subject. E is equal to K M over Km over T squared. So we want percentage uncertainty. So the percentage uncertainty in E is going to be percentage in K plus percentage in M plus twice because of the power on T, percentage in T. So we substitute, that would be 2.1 plus 0.6 plus 2 times 1.5. So that is 2.7 plus 3, that is 5.7. 5.7%. Use your answer in B to determine the value of E with its absolute uncertainty. They gave us the value of E as 8.245. So we shall get the absolute in E, which is the percentage 5.7 over 100 times the value of E, which was given as 8.245 times 10 power 9. So from my calculator, 5.7 times 8.245 exponent 9 divided by 100. So this is 4.7. It's 4.7, that is 3, 6, 7, 8. 4.7 times 10 power 8. Note that the other true value was to power 9, so I must write this also to power 9. So I will move one step to the left. So it is 0.47 times 10 power 9, which is approximately 0.5 to one significant figure times 10 power 9. So it is one decimal place, 0.5. It is one decimal place, so I'll write the answer as 8.2 to one decimal place. But this is times 10 power 9. Oh, the power 9 has been written there, so I don't need to repeat myself. It is written there. So let me rub off this. Last but not least, a solid metal sphere has diameter of 3.42 plus or minus 0.02 centimeters and a mass of 67 plus or minus 2 grams. Calculate the density. So we know density is mass over volume. And it is a sphere. It is a metal sphere. So we know that the volume of a sphere is 4 over 3 pi r cubed. So density is equal to, I'm substituting for the volume, 3 goes up, 3m divided by pi r cubed. But remember, r is diameter over 2. R is diameter over 2, r is d over 2. So I'm substituting. The density is going to be 3m divided by pi into d over 2 raised to power 3. So we have density as 3m divided by pi d cubed over 8. So 8 goes up. 8 goes up. Oh, so there is a 4 pi here. There's a 4 pi here. So 4 cancels that, it becomes 2, and the 2 goes up. So density is going to be 6m. The 2 goes up, so it is 6m over, there's a pi there, pi d cubed. So I did this so that calculating the uncertainty becomes easy. Now let's substitute. Density is going to be mass, 6 times the mass. We want the answer in grams, so we don't convert. 67 divided by pi times d, which is 3.42 power 3. So from the calculator, 6 times 67 divided by pi times 3.42 cubed. So the density is 3.199, or approximately 3.2. Lastly, determine the percentage uncertainty in the density. So I have already manipulated my expression to look like this. Density is equal to 6m over pi d cubed. So it is now easy to find a percentage uncertainty. So percentage in density is going to be absolute in M over M plus 3 because of the power absolute in D over D. Then I'll multiply this by 100 to get percentage. So this is for mass, I think it was 2 over 67 plus 3 times D 0.02 over 3.42, and this is multiplied by 100. So I have open brackets 2 divided by 67 plus 3 times 0.02, that is 0.06 divided by 3.42 times 100. So that is 4.7. So since it is just percentage, that will be 4.7%. So that is the end of physical quantities and units. See you in the next chapter. Bye bye.